Welcome to the fifth lecture of EMTH4, Engineering Data Analysis. We are still in the topic of probability. And in this lecture, we will cover the counting techniques useful in probability. The idea is to simplify the counting of elements of our sample space, since in the real world, events cannot be simplified to a mere toss of a coin or the rolling of a die or two dice event. In research, it is normal to encounter large sample spaces. All right. So far, we have only made reference to a single coin toss and single die roll experiments. Let us expand the coin toss experiment first by tossing two coins instead of one. If you have indistinguishable coins, okay, since they are two identical, and it would be too hard to differentiate them from each other with the naked eye, we have its sample space of possible event outcomes as the set containing HH, TT, and D. Okay. Again, H is for head and T is for tail. T is what? This time representative of a head tail or tail head result, meaning indistinguishable. Okay. So we are unable to determine which coin is which. So to forego the order of their appearance, we use a notation D. Okay. If the coins are distinguishable, their order is now of importance. So the head, tail, and tail head events become unique and distinct. The sample space then becomes, as expected, D is differentiated into HT and TH. Now, what happens to the sample space if we have now a 10 coin toss? We have done a 2 coin toss and identified the sample spaces to contain 3 and 4 elements or outcomes for the indistinguishable cases, respectively. Okay, so what happens now if there's a 10 head coin toss? We have so far listed sample spaces containing very few elements or outcomes. We proceed with simple counting aids with the use of an organized table and another visual approach called the tree diagram. Okay, it's shown in figures 1 and 2. These two methods enable us to list all elements or outcomes there are in a, for example, in the coin toss. Okay, in the tabular representation, the two numbers of elements or possibilities for each coin is listed in a similar to a multiplication table. The cells corresponding to the intersections of the elements then get the elements in them, so that it seems that each element is multiplied to each other, as in H times H or HH. In the tree diagram, we start with the outcomes of one coin, but we then introduce the second coin of outcomes, okay, to each outcome of the first coin. It is multiplying, the two. It is like multiplying the two for the outcomes of the first coin with another two representative of the second outcomes of the outcomes of the second coin. So we get 4 for the outcome of the tossing two coins, similar to the output of the tabular counting. What happens now if two activities are done in succession to comprise a random experiment? This is the case of drawing two balls in succession, where the drawn ball is returned to the collection drawn. What are the elements of the sample space for this kind of random experiment? Now, using the table and tree diagram methods, we have the results as shown. For the table, we fill up the rows and columns with the elements beginning with the first row and first column, and we multiply those elements element to element. Okay, we get the resulting table where the combination of R, B, and Y or elements or our outcomes are seen. The same goes with the tree diagram. We begin with the first collection of RBY balls, and then list out the RBY combinations for each of the first RBY balls. And we do so by branching out from the first RBY balls, okay, and then branching out again for the second set of RBY balls. The resulting combinations or outcomes are shown to be the same with the result of the tabular method. Okay, we list the combined elements or outcomes in the set notation, and we get the final answer with 9 elements as shown. Okay, RR, RW. Okay, my apologies, that should be RBY. Okay, but let me just correct that one. So I've corrected it. Okay, now we have already talked about 2 solutions, but these solutions of tabular and tree diagram methods will still fall short if we have the following case. Okay, how many numbers in the range 10,000 to 99,999 with no repeated digits? And also, how many license plates with 3 letters following 3 digits? Okay, how many plates are there, available plates? The multiplication rule is a mathematical approach to the tabular and tree diagram, and it's a way to simplify the notation. Okay. It is defined such that a random experiment with k steps or succession, of which the first can be made in n1 ways, and for each of these, the second can be made in n2 ways, and for each of this, the kth can be made in n sub k ways. Then the experiment outcome can be made in n1 times n2 times all the way to the nk ways. Okay, until the last or kth step or succession can be made in ways for the outcomes. So just before it, okay, we have k minus 1. Okay, let us try this problem to solve the 2 examples. Okay, how many numbers in the range 10,000 to 99,999 with no repetition of digits using the multiplication rule? For the first problem, the steps or successions are attached to the digits or of the numbers. Also, for the first, for the given set of numbers, there are 5 steps. Okay, for each of there are 5 digits. Okay, so there are 5 steps. The first will have what? 9 choices, outcomes. Okay, there are supposedly 10 outcomes, but 0 is disregarded. Why? Because it becomes 4 digits already if 0 is included. Okay, so we leave out 0. So we have 9 outcomes, numbers 1 to 9. Now, the second step will also have 9. Okay, given that 1 has been exhausted already. The third will have 8. Okay, 8, which is 10 minus 2. The fourth will have 7. Okay, and the fourth will have 6. Okay, multiplying will yield these numbers. Okay, multiplying them will yield the number, the sample space. Okay, which is what? Okay, 9 times 9 times 8 times 7 times 6, which will be 27,216. Okay. Why? Because there's no repetition of digits. Okay, for the second example, on the license plate, consisting of 3 letters and 3 digits, the 3 digits succeeding the letters, the total number of the steps is 6. For the first 3 steps comprising letters, given, okay, we have an English alphabet, not the Filipino alphabet. So having 26 letters, each will have 26. So 26 outcomes or choices. So all 3 will have 26 times 26 times 26. The fourth up to the 6 steps will each have 10 steps. Why? Because we have 0 to 9, the digits 0 to 9. So we have 10 outcomes. So the answer would be the number of the elements of the sample space would be 26 times 26 times 26 times 10 times 10 times 10. And that should give you 17,576,000. Wow, that's a lot of vehicles. I don't know if EDSA could contain that. Another counting technique is permutation. By definition, permutation given by a derived equation shown, okay, yields the number of arrangement of objects from a set of objects which are distinct, unrepeated, and ordered in arrangement. So take note of that, distinct, unrepeated, and ordered. The equation considers the number of objects to be taken denoted as K, and the total number of objects to be selected from denoted as N. Here's an example where we suppose there are 100 varieties of tomatoes commercially available, and that the yield improvement study we have earlier talked about back in lecture 1 desires to select only the top 3 varieties for the study. What is being asked is the total number of combinations there is from among the 100 varieties available, and from which the top 3 will be taken from. This is a direct use of the derived permutation equation. Okay, so we have the equation. We simply make 100 and K equals to 3. Thus, the formula becomes 100 factorial over the factorial of the quantity 100 minus 3. Okay, the quantity in the denominator simplifies to the factorial of 97. And dividing the numerator by the denominator, okay, cancels the 27 factorial of the numerator, thus leaving us with 100 by 99 by 98. Multiplying, the result is still a big number. It's 170,200. Another counting technique is combination. Unlike permutation, does not consider the position. Okay, so the order of the outcomes. The equation takes in the number of objects to be taken, denoted by K, and the total number of objects to be selected from, denoted as N. And to disregard the order K, K factorial is introduced in the denominator. Okay, so the denominator cancels the K factorial, that cancels the order. So the final formula is the permutation formula, further divided by the K factorial. Here's an example from sports. In a basketball tournament, the total number of games the teams will play in a round-robin format is being determined. How many games should be held in this kind of format? To solve for the number of outcomes for the given event using the combination equation, we take 10 as N and 2 as K. So it's already shown using the permutation formula, the given N and K yields a total of 90 possible outcomes. In the tournament though, the order of the team does not matter. Thus, the permutation output still needs to be divided by K factorial, or which K, we have K 2 as K, so 2 factorial. And we have to divide the result by the 90 by the 2, and we have the number of elements 45. So the tournament will have each of the 10 teams play other teams in 45 games. The last counting technique is the iteration of, it's an iteration of permutation. It's permutations with non-distinct items. This the iteration of the permutation technique allows for cases where or when some individual outcomes have no distinctness or outcomes that are similar to each other in the set out of the outcomes. Okay, so in this case, the order is still considered. The denominator of the permutation equation becomes the product of the factorial of the individually distinct outcomes. An example is you consider a class of 10 students and there are two sets of twins. And in how many ways can the students be seated such that the twins can be seated regardless of their first names? Twins will have the same surnames. Okay. Thus, okay, in the class, okay, the first two numbers will be the factorial of 2. Then there will be 6 other unique items that will be placed anywhere in the seat. Okay, this will yield, okay, 20 factorial over 2 factorial, the quantity 2 factorial times 2 factorial times 1 factorial, 1 factorial. Okay, so we have 6 items there at the bottom. That is 1 factorial. And simplified, this will result to, okay, 3,628,800 over 2 over 2. Okay, and the number of elements should be 907,200. In the next lecture, we will cover the rules of probability.